In this video we're going to do question 5 of the 2014 step 2, and this question is probably the easiest one of the paper, and it's all about solving a differential equation in part 1, and then part 2 is about manipulating and using smart substitutions to use the result found in part 1 and solve part 2. So let's start with part 1. So before doing part 1, we're told given that y equals xu, where u is a function of x, write down an expression for dy dx. So we have y equals xu, and so therefore dy dx, if we use the product rule, so it's the derivative of x with respect to x, so 1 times u, plus the derivative of u with respect to x, so du dx, times x. So there we go, that's our dy dx. And now we're told, using the substitution y equals xu, solve dy dx equals, so solve this differential equation, equals 2y plus x divided by y minus 2x, given that the curve passes through the point 1, 1. And so that last condition will be used at the end to calculate the constant of integration. So our differential equation is dy over dx equals 2y plus x divided by y minus 2x. So if we use a substitution y equals xu, so we've already calculated that dy dx becomes u plus du dx x. So we have u plus du dx x. And so this is equal to 2xu plus x divided by xu minus 2x. And so here the x's cancel because we have u plus du dx times x is equal to, in the numerator we have x times 2u plus 1 divided by x times u minus 2. So the x's cancel, and if we bring u to the other side, we have du dx x is equal to 2u plus 1 minus u times u minus 2 divided by u minus 2. So we can calculate, expand and simplify the term on the right. So we just have 2u plus 1 minus u squared plus 2u. So it's 1 plus 4u minus u squared over u minus 2. Okay, and now we're going to take the dx to the other side, and this fraction over here. So we have u minus 2 du over 1 plus 4u minus u squared is equal to dx over x. And now we're just going to integrate both sides. So the integral, so we're going to do a little trick. We're going to, well, first I'll write. So we're doing the integral of u minus 2 with respect to u of 1 divided by 1 plus 4u minus u squared, and the integral of dx over x. Now the term on the right is easy. It's just ln x. The term on the left, now we notice that the derivative of the denominator is 4 minus 2u. And 4 minus 2u is very close to u minus 2. All we need to do is multiply by minus a half. So if we take a factor of minus a half out, then our numerator will become 4 minus 2u, because 4 times minus a half is minus 2, and minus a half times minus 2 is 1. du over 1 plus 4u minus u squared. And we leave the right side equal. And so therefore, the left side, when we integrate, becomes ln of 1 plus 4u minus u squared is equal to ln x plus our constant, c. So we multiply by minus 2, the equality, so we just get 4u minus u squared equals minus 2 ln x plus c, because yes, it has a different value, this c and this c, but it's still just a constant, so we can leave it as plus c. And we're actually going to write c equals ln of a, because that's also a possible constant. And so we have ln of 1 plus 4u minus u squared is equal to ln of x to the power of minus 2 plus ln of a, just another constant. And so ln of 1 plus 4u minus u squared is equal to ln of a over x squared. And the reason we did all this manipulation is because now we can take the exponential of both sides to cancel out the ln's. So if we exponential both sides, we get 1 plus 4u minus u squared equals a over x squared. And so now we can remember that our substitution was y equals xu, which means that u equals y over x. So we can substitute squared, and that's equal to a over x squared. And now we multiply everything by x squared. So we get x squared plus 4xy minus y squared equals a. And so now we're going to use the condition that our line or our graph passed through the point 1, 1, which means that we have 1 plus 4 minus 1 equals a. Therefore, a equals 4. So the equation of our line is x squared plus 4xy minus y squared equals 4. And this is indeed, as they said, a quadratic in x and y. So now for part 2, we're told using the substitutions x equals big X plus a and y equals big Y plus b, for appropriate values of a and b, or otherwise, solve this new differential equation, dy over dx, x minus 2y minus 4, and 2x plus y minus 3. And it passes through point 1, 1 again. And we notice that without the minus 4 and minus 3, both expressions they're different, but are very similar. And so the idea is by doing the substitution x equals big X plus a and y equals big Y plus b, we're going to get rid of the minus 4 and of the minus 3. So we want to get x minus 2y. So it's x minus 2y minus 4 equals x minus 2y. And 2x plus y minus 3, 2x plus y minus 3 equals y plus 2x. And now we're told to use a substitution x equals big X plus a. So if we take the first equation, if we take the first one, we have x plus a minus 2y minus 2b minus 4 equals x minus 2y, and therefore a minus 2b equals 4. And the second equation, we have 2x plus 2a plus y plus b minus 3 equals 2x plus y. And so 2a plus b equals 3. And so by solving these simultaneous equations, we get that a equals 2 and b equals -1. Okay, so we're going to do the substitutions. X equals x plus 2 and y equals y minus 1. Now, before we can do that, because initially our differential equation was in terms of dx dy, we need to get it in terms of dx dy. So big X, big Y. So if we're going to differentiate, so we're going to take this equation and differentiate with respect to small x. So the left side is just 1 is equal to d big X over d small x, and the 2 doesn't differentiate. And so we just get dx equals d big X. And in the same way, we'll get small y equals big Y. D small y equals d big Y. So now we're ready to rewrite. So we now can rewrite our differential equation as as d big Y d big X is equal to x minus 2y over 2x plus y. So that's good. It's very good. The only problem is that in part 1, we had solved a differential equation which was dy dx is equal to, the one we had solved was 2y plus x, and in the denominator, y minus 2x. And so if we look carefully at the 2, we actually realize that if we put big X equals minus small x, we get the same thing on the right. And so we're going to use the substitution x equals minus k. Okay, so therefore 1 equals minus dk dx. So which means that dx equals minus dk. And we're gonna plug it into this equation. So we have minus dy dk is equal to minus k minus 2y over y minus 2k. There we go. And so now if we multiply everything by minus 1, we have k plus 2y over y minus 2k, or if we flip sides, is equal to dy dk. And now we're in exactly the same configuration as in part 1. And so we know that the solutions to this differential equation are of the form x squared plus 4 k squared plus 4ky minus y squared equals c. So we know this. So now we need to convert back. So this is big Y and big Y. There we go. So now we need to convert back to small x and small y. So the first thing is we know that k equals minus big X. So we can rewrite it as x squared minus 4xy minus y squared equals c. And then we use the substitutions. We had x equals x plus 2. And we had y equals y minus 1, which means we have x equals x minus 2 and y equals small y plus 1. So if we plug this in, we have x minus 2 squared minus 4x minus 2 y plus 1 minus y plus 1 squared is equal to c. And so we can expand. We have x squared minus 4x plus 4 minus 4xy minus 4x plus 8y plus 8 minus y squared minus 2y minus 1 is equal to c. And so if we just group terms, so we have x squared minus 4x, so minus 8x, x squared minus 8x, minus y squared plus 8y minus 2y, so plus 6y, minus 4xy equals 4 plus 8 minus 1, so plus 11 equals c. So now the last thing we need to do is calculate c, and we know that our graph passed through points 1, 1. So we have 1 minus 8, minus 1 plus 6, minus 4 plus 11 equals c. And if we use a calculator, because we're lazy, we get that c equals 5. C equals 5. And therefore, our final equation is x squared minus 8x minus y squared plus 6y minus 4xy plus 6, because 11 minus 5 equals 0. And so that is the solution to part 2.